Hello everyone, I am Dr. Sirajul Faisi. I welcome you in my YouTube channel. Today in this video, we are going to learn about P-block elements. I have already uploaded one video on P-block elements. So I would suggest please go through my previous video and then you will continue with this video. So let us start. Today I will discuss about the introductions of group 14 elements occurrence. So carbon, silicon, germanium, tin, lead, non-metals, metalloid, metal. You can see the chemistry gives 10 lesson. How you remember? Chemistry sir gives 10 lesson. Chemistry for C, sir silicon gives G, 10 means tin and lesson means lead. So just remember this quote, chemistry sir gives 10 lesson. Chemistry sir gives 10 lesson. So isotopes of carbon, stable, unstable. You can see carbon 12, carbon 13 and carbon 14. Carbon 14 reactive, radioactive. 6 protons, 6 neutrons, 6 protons, 7 neutrons, 6 protons and 8 neutrons. You see the carbon 17th most abundant element by weight, elemental state and combined state. So elemental state, coal, diamond, graphite. Combined state, hydrocarbons, carbon dioxide, carbonates. So combined state, fats, proteins, minerals, petroleum, fossil fuel, vitamins, carbohydrates. So silicon, second most abundant element by weight, silicates and silica. So quartz and sand, you can see example. Occurs in traces 1.5 meter. Ultra pure germanium and silicon are used in making transistor and semiconductor devices. So germanium occurs in traces 1.5 ppm. Tin, stone or cassiterite SnO2 and lead, galena, PBS. Now electronic configuration, you can see 2p2 for carbon and so on. Electronic configuration, the inner core of the electronic configuration of element in this group differs. So electronic configurations 2p2, 3p2, 4p2, 5p2, 6p2. So carbon and silicon have inert gas core. You can see 2p2, 3p2. So atomic radii, you can see increases 77, carbon, silicon 118, germanium 122, tin 140, lead 146. So atomic radii increases from top to bottom. Atomic radii increases. You can see after silicon, the increases is small due to the ineffective shielding by the D and F electrons. So you can see 122 and 146. Very little differences due to D and F electrons. So after silicon, increases is small due to ineffective shielding. That word is important. Ineffective shielding. Just remember, ineffective shielding by D and F block elements. Electronegativity measures the tendency of an atom of an element to attract pair of electrons. This phenomenon you know. So smaller the size of atom, greater the electronegativity. Electronegativity, carbon 2.5, silicon 1.8, germanium 1.8, tin 1.8 and lead 1.9. So electronegativity decreases from carbon to silicon, but then from silicon to tin remains almost constant and increases marginally for lead. Ionization enthalpy. Ionization energy is the amount of energy required to remove the most loosely bound electron from the valence shell of an isolated gaseous atom. So ionization enthalpy, you can see 1086, 786, 761, 708 and 715 from carbon to lead. So atomic size increases, shielding effect decreases, energy required decreases. So You can see ionization enthalpy decreases from carbon to silicon, silicon to tin decreases, and marginally increase for lead. So general trend in group 14 elements, inner pair effect. It is the reluctance of an H2 electron to unpair and participate in chemical bond formations. So inert pair decreases in shielding between the valence electron and noble gas core. The number of electrons in d and f orbital increases. So tendency to release 2 electrons increases while tendency to release 4 electrons decreases. So inner pair effect, and hence inert pair effect increases from germanium to lead. Now oxidation state, stability +2 increases. You can see general electronic configuration GEC, NH2 and P2. So ground state +2 and excited state +4, inert pair effect. You can see oxidation state +4, carbon greater than silicon greater than germanium, tin, lead. So group 14 carbon, silicon, germanium, tin, lead, oxidation state +4, -4, +4, +4, +2, +4, +2, +4, +2. Stability, stable, more compound, few compounds, stable. So reducing agent and oxidizing agent. You can see, friends, the sp3d2 hybridization available of d orbitals. So in silicon, stable silicon F6 to minus, germanium Cl6 to minus, tin hydroxide SnOH whole 6 to minus. Stability, PbX2 more stable than PbX4. As we move down the group, oxidation state +4 to +2 more stable. So anomalous behavior of carbon, catenations, allotropes of carbon. So friends, anomalous behavior, absence of d orbitals, very small atomic size 77 picometer, atomic radii, you can see carbon, and then increases silicon, germanium, tin, lead. Absence of d orbitals, very small atomic size and very high electronegativity 2.5. You can see very high ionization enthalpy 1086 kilojoule per mole. So points of difference, because of smaller size and lowest atomic volume, carbon is the hardest element in the group 14 family. Among the elements of group 14, carbon has the highest melting and boiling point, highest ionization enthalpy, and most electronegative element of this group. Due to absence of the orbitals, it has no tendency to form complex ion. So points of difference, carbon has tendency to form double and triple bond, forms alkene and alkyne. Properties of catenations, carbon show many allotropes. So what is the catenations? The properties of self-linking of atom of an elements to form a state or branch chain and ring of different sizes by covalent bond is called catenation. You see the linear chain, branch chain, cyclic compound, order of catenations. As we go down the group, element-element bond energies decreases rapidly. So order of catenations, you can see bond enthalpy, carbon 348, silicon 297, germanium 260, tin 240, and lead 81. So since the bond energy of carbon is very large, carbon has maximum tendency to form chains, the tendency for catenation decreases in the order. So allotropes of carbon, crystalline and amorphous, lamp black and charcoal, wood charcoal and animal charcoal, crystalline, diamond, graphite and fluorine. So some important compounds of carbon, diamond and graphite. You know, parameter value of diamond, carbon-carbon bond, covalent, carbon-carbon bond length 154 picometer, melting point 3873 and density 3.51 gram per cubic centimeter. So diamond, you know, ground state and excited sp3 hybridized tetrahedral geometry. You can see. So uses, diamond is used in jewelry and also in precious gems. Diamond is used and abrasive for sharpening hard tools. Diamonds also used in manufacturing of tungsten filaments for electric bulb. Diamond is used for making board and for rock drilling. So graphite 2D structure, sheet are fused, planar hexagonal ring, each carbon bonded to 3 other carbon. So this is the graphite hybridizations, ground state, excited state, hybridized state, you can see. So graphite structure, physical properties, form 3 sigma bond, 4th electron form pi bond, electrons are delocalized throughout the sheet, layers are held together by van der Waals force of attractions, carbon-carbon bond length 141.5 picometer, distance between layers 340 picometer. So uses, graphite is soft, slippery, so used as a dry lubricant instead of oil. As graphite can conduct electricity, it is used to prepare electrodes. When mixed with wax or clay, graphite is used to make ores of the lead pencil. Graphite is also used in the manufacture of dry cells and batteries. So these are the differences between diamond and graphite. Hard, white and crystalline solid, soft, gray and crystalline solid, regular tetrahedral structure, hexagonal planar structure, each carbon attached to 4 other carbon, each carbon attached to 3 other carbon, all electrons bonded. So diamond is a bad conductor of electricity. Here carbon contains a free electron, so graphite is a good conductor of electricity. So the carbon-carbon bond length is 154 picometer, carbon-carbon bond length is 141.5 picometer, 3D network of carbon, cage-like structure, layered structure. So you see the fluorine are cage-like molecules, 60 vertices, each one occupied by 1 carbon atom. Carbon 60 molecules shaped like social ball, Buckminster fluorine. Molecule is composed of 20 hexagon and 12 pentagon. A 6-member ring is fused with 6-member or 5-member ring, but 5-member ring can only fuse with 6-member ring. The structure sp2 hybridized, each carbon forms 3 sigma bond with 3 other carbon atom, contains both single and double bonds. Remaining electron is delocalized, which gives aromatic character of fluorine. So fluorine preparation, graphite, electric arc, helium or argon, vaporized carbon, condense, fluorine shoot, C60, little C70, chromatography over aluminum oxide, you will get the fluorine C60 and C70. Properties, fluorine being covalent are readily soluble in organic solvent. Fluorine react with group 1 metal forming K3C16 solid, which behaves as superconductor below 18 kilo. So fluorine is spherical and cylindrical, Bucky balls, and carbon nanotube, Bucky tube. So planar fluorine graphene, it has densely packed honeycomb crystal lattice, carbon-carbon 143 picometer and carbon double bond 138 picometer. So uses, diamond is a precious stone used in jewelry, 1 carat 200 milligram, graphite electrode in battery and also industrial electrolysis, used to prepare crucible in laboratory as they are inert toward the acid and alkalis. Charcoal, activated charcoal is used as a good absorbent for the absorbing poisonous gases and removing coloring impurities from water. So carbon black used in the manufacture of black ink and pigment. Coke is used as fuel and act as a reducing agent in metallurgy. Fibers embedded in plastic material form high strength, lightweight composite. Fishing rods, tennis racket, aircraft and cannons. So friends, I will talk about the preparation of wood charcoal and lamp black in next video. So if you like this video, then subscribe my channel and thanks for watching.